The world of technology is changing, and in a fascinating breakthrough, scientists have developed a tiny robot that can transform its shape by melting and then reforming itself just like a sea cucumber. This remarkable ability allows the robot to navigate through narrow spaces and even escape from confined areas, similar to how a jailbreak might happen in the movies. The team conducted tests to examine how well the robot can move and change its shape, and they recently published their findings in the prestigious journal Matter. Though it might seem like a concept straight out of science fiction, the inspiration for this unique robot comes from a real-life marine creature, the sea cucumber. Because these fascinating animals have the incredible ability to rapidly and reversibly alter their stiffness. Drawing inspiration from nature, the researchers aim to recreate this shape-morphing behavior in soft materials for engineering purposes. This innovative approach holds great promise for creating robots that can efficiently navigate and adapt to various challenging environments. Conventional robots have been characterized by their stiff and hard metal body designs, which unfortunately restrict their ability to maneuver effectively through confined or tight spaces. This limitation poses significant challenges when attempting to deploy robots in environments that demand agility and adaptability. On the other hand, soft robots, constructed from more pliable materials, offer enhanced flexibility and deformability, enabling them to navigate through irregular and cramped spaces with relative ease. However, their softness comes at cost, reduced strength, and difficulties in precise control, which makes them less suitable for certain tasks that demand robustness and accuracy. To address this dilemma and push the boundaries of robotics, the ingenious team of researchers embarked on a mission to create a robot that could seamlessly transition between liquid and solid states. This remarkable robot possessed the amazing ability to transform from a liquid, malleable state, ideal for navigating tight spaces, to a solid, rigid state, granting the robot the necessary strength and stability to undertake demanding tasks effectively. Now, the metal used to create this robot is called gallium. This metal possesses a relatively low melting point, approximately 86 degrees Fahrenheit, making it ideal for their purposes. To enhance the robot's versatility, they incorporated magnetic particles within the gallium structure. Thanks to this ingenious addition, scientists can exert precise control over the robots using magnets. With this magnetic manipulation, the robots can be prompted to move, melt, or stretch as required for their intended tasks. By achieving this delicate balance between strength and flexibility, the team has opened up new possibilities for creating a new generation of robots that can adeptly adapt to a wide array of environments and challenges. This groundbreaking advancement promises to revolutionize various industries, from search and rescue missions in complex terrains to exploration tasks in distant and hazardous locations. In addition to their extraordinary shape-morphing capabilities, these robots possess a fascinating feature powered by the integration of magnetic particles into their structure. These magnetic particles endow the robots with the ability to interact with an alternating magnetic field, one that changes over time. When exposed to this dynamic magnetic field, a remarkable phenomenon occurs within the robot's metal composition. The presence of magnetic particles within the material triggers an interesting chain of events. As the alternating magnetic field induces a response in the metal, it generates an electric current. This electric current in turn causes an increase in the metal's temperature. The process is akin to how an electric coil in a stove heats up when electricity flows through it. Leveraging this unique magnetic effect, the researchers have ingeniously harnessed the induced heat to initiate a controlled phase change in the material. Essentially, the material can undergo a transformation from solid to liquid, effectively melting into a malleable state. This phase transition is skillfully brought about through the process of induction, where the heat generated by the electric response alters the material's internal structure. However, the transformation is not permanent. After the material has served its purpose, it cools down naturally due to ambient conditions. The cooling process prompts the material to solidify once again, resuming its original state. Such a complex yet elegantly designed system led the research team to call their invention a magnetoactive liquid-solid phase transitional matter. During an array of comprehensive tests, the innovative robot showcased extraordinary capabilities. It demonstrated compressive ability, including jumping up to 20 times its own body length, scaling walls with agility, deftly soldering a circuit board with precision, and even successfully escaping from a simulated prison-like confinement. What's more, in its solid state, the robot displayed exceptional strength, effortlessly supporting an object approximately 30 times its own weight, as revealed in the study's findings. What's more fascinating is that, according to the researchers, this groundbreaking technology holds great potential for applications in the biomedical field. To demonstrate its capabilities, they conducted a fascinating experiment using the robot to extract a ball from a model human stomach. The ingenious solid robot swiftly moved towards the ball, cleverly melted itself to encase the object, and then smoothly reformed into its solid state, effectively carrying the ball out of the model. During this test, the researchers employed gallium as the material for the robot. However, they acknowledged that a real human stomach maintains a temperature of approximately 100 degrees Fahrenheit, which surpasses the melting point of gallium. Nevertheless, the team proposed a promising solution by suggesting the incorporation of other metals into the material, thereby elevating its melting point and enabling it to operate flawlessly in the human body's warmer conditions. With such remarkable adaptability and ingenuity, this technology could revolutionize medical procedures and offer exciting possibilities for treating conditions within the human body that were once considered challenging to reach or address effectively. While soft robotics researchers continually explore novel materials, the real breakthrough lies in the artful integration of these innovative substances. Looking ahead, the gallium robots hold great promise in various applications. The team envisions their potential in assembling and repairing hard-to-reach circuits or serving as universal screws that can morph into screw sockets when needed. However, before these robots can be safely used in medical settings, scientists must tackle the challenge of precisely tracking their position within a patient's body. Now, to be honest, sometimes it does look scary, like all these artificial intelligence getting popular at what they can do. But the main question is, are they evolving? What if someday they somehow do that one thing that the entire mankind is scared of, becoming conscious? What if I told you that they already became sentient when Google's and Microsoft's AI program actually started saying things that don't make sense? Check this video to find out.